What if the rules of reality you assume are not actually laws, but temporary guesses? For centuries, explanations of the cosmos, the body, and the elements rested on inherited authority that seemed inviolable. Then, one daring era rewrote almost everything. Mathematicians, natural philosophers, and explorers began to replace authority with evidence, line by line, law by law. What they uncovered restructured knowledge and changed what it even meant to know. This is not just a story of discovery. It's the story of how humans learn to step outside of tradition and dare to question existence itself. Hey everyone, thanks for tuning in. Before we begin, just a quick housekeeping note. If you enjoy what I'm doing, a like and subscribe would be really helpful. It goes a long way in keeping the channel going. And don't forget to drop a comment. I'd really love to know what you think. In medieval Europe, knowledge was often viewed more as an inheritance than a discovery. A student in a lecture hall would listen as a master read from Aristotle or Galen, not to invite debate, but to reaffirm tradition. Illness was explained through the four humors: blood, phlegm, yellow bile, and black bile. A fever indicated excess heat in the blood, whereas melancholy was seen as an overabundance of black bile. These models dominated teaching, although a few physicians quietly experimented at the bedside. The heavens were also depicted through philosophy rather than direct observation. The Earth fixed at the center, with the planets and stars carried on transparent spheres. Challenging any of this was to question both classical authority and Christian theology. Such a framework provided certainty, but little space for curiosity. A comet in the sky was not a puzzle for study, but a divine sign. A new disease was fitted into the humoral scheme rather than prompting reconsideration of the existing framework. Medieval classrooms valued repetition over revision. Students memorized but did not test. As a result, the protection of knowledge blurred into the prevention of change. The invention of the printing press altered the rhythm of history. Texts could now circulate across Europe, no longer confined within lecture hall walls. Diagrams, anatomical sketches, and star charts appeared in multiple copies, revealing errors clearly. Ideas could be compared and debated by readers separated by distance. Knowledge began to behave less like a fixed property and more like a shared debate. And unlike tradition, such a debate could not always be controlled. Exploration pushed these limits further. Voyages brought back foods, plants, and animals that did not fit into Aristotle's tidy categories. Suddenly, new species appeared that no ancient author had described. Some regarded this as evidence of God's abundant creation, but others saw it as proof that inherited catalogs of nature were incomplete. Authority alone could not account for the growing evidence from the wider world. Medicine also faced these shocks. Travelers reported remedies from distant cultures that cured diseases humoral theory could not treat. Plants from the Americas entered European practice, undermining centuries of accepted recipes. Physicians faced a difficult choice: trust Galen's writings or trust actual results in the sick room. These often conflicted. The Renaissance deepened these fractures. Humanist scholars examined original Greek and Latin texts, comparing them with later commentaries. They uncovered distortions, mistranslations, and even fabricated editions. Instead of strengthening certainty, this discovery weakened it. Authority was being challenged, not only by new evidence, but also by the realization that existing authorities had been altered over centuries. The Reformation added further pressure. Encouraging individual reading and interpretation casts doubt on the central institution that had protected learning for centuries. Knowledge no longer flowed solely from one authority. Disputes could no longer be settled by pronouncing what the Church or Aristotle had said. A culture of questioning spread, affecting not only theology, but also science. The Catholic counter-response sought to reinforce order. Through censorship, the index of forbidden books, and the punishment of dissent, many thinkers continued to face risks in challenging entrenched systems. Yet curiosity proved difficult to suppress. Even the heavens began breaking the old mold. New stars appeared where Aristotle had promised perfection. Comets crossed the sky in defiance of the circular paths meant to define celestial harmony. Reality was slowly refusing to follow the rules set for it. By the mid-16th century, the pressure was impossible to ignore. In 1543, Copernicus published his vision of a sun-centered cosmos, and Vesalius released his detailed anatomical drawings, both revealing deep cracks in the old order. What had once been regarded as unquestionable wisdom now appeared unstable. The neat structure of spheres and humors no longer matched the increasing body of evidence. Authority and observation had entered into open conflict. Europe now found itself divided between two ways of understanding the world. Doctors still explained sickness through humors, and philosophers still believed in a fixed, crystalline cosmos. But travelers, presses, and early scientific instruments steadily eroded trust in those views. Facts accumulated that no commentary could dismiss. Sooner or later, someone would need to decide whether to defend tradition or follow evidence wherever it led. That moment called for individuals willing to take a stand and speak out. People are ready to suggest ideas that seemed unthinkable. And in the years that followed, such figures began to emerge. The individuals who transformed knowledge are often remembered as visionaries, but during their own time, they were voices of disruption. The founders of the scientific revolution challenged inherited knowledge, tested claims against evidence, and accepted personal risk when tradition resisted. Their stories remind us that science is not only about making discoveries, but also about making decisions in the face of uncertainty. Nicholas Copernicus is often seen as the quiet start. A scholar and churchman in Poland, he spent decades working on a manuscript that placed the sun, not Earth, at the center of the cosmos. Published in 1543 as De Revolutionibus Orbium Coelestium, it offered a system that felt simple, ordered, and daring all at once. Copernicus was cautious, releasing his work only late in his life. His tables were useful even to critics, but few accepted the broader conclusion. It was less an apparent rupture than a seed waiting for others to defend it. That same year, Andreas Vesalius brought courage to the field of medicine. His On the Fabric of the Human Body peeled back centuries of reliance on Galen. Vesalius performed dissections himself and revealed how much earlier accounts had erred because Galen's understanding was based on animal anatomy, not human anatomy. The book's detailed illustrations compelled students and doctors to examine the body directly, rather than accepting inherited texts. Critics accused him of arrogance, but Vesalius demonstrated that the body's truth lies in observation, not tradition. Francis Bacon presented a vision of how inquiry itself should be reconstructed. In Novum Organum, published in 1620, he promoted experiment, induction, and careful reporting rather than elaborate argument. Bacon himself made a few scientific discoveries. His strength was in demanding a method that rejected pointless speculation. Knowledge to him must be built from facts, not rhetoric. This approach later shaped institutions like the Royal Society, where observation and experimentation were shared to achieve collective progress. Galileo Galilei took evidence directly to the eye. Using his telescope, he observed mountains on the moon, sunspots on the sun, and the 4 bright moons orbiting Jupiter. These observations shattered the belief in celestial perfection, showing that Earth was not the only world with satellites. When he defended heliocentrism in his Dialogue, published 1632, authorities accused him of heresy. Condemned a year later to house arrest, Galileo paid the price for asking influential figures to see what was plainly in front of them. Yet, his observations changed Europe. Johannes Kepler turned patience into a breakthrough. Using Tycho Brahe's detailed measurements, he developed 3 laws of planetary motion between 1609 and 1619. Planets moved in ellipses, not circles, with speeds that varied in a perfect ratio to their distance from the Sun. This shattered Aristotle's insistence on uniform circular motion. For Kepler, mathematics was the music of creation. His work gave precise form to Copernicus's vision and provided the framework that Newton would later link to a universal law of gravity. René Descartes sought certainty in an age of doubt. In his Discourse on Method, published in 1637, he outlined 4 steps: accept nothing unproven, break problems into parts, proceed step by step, and review carefully. He championed deductive reasoning and developed analytic geometry, merging algebra with geometry into a new mathematical tool. To him, the universe resembled a machine made of parts and motions. Even animals, he argued, were automatons composed of matter. Some found this reductionist, but it provided clarity on how thought and nature could be understood rigorously. Each of these thinkers paid a price. Vesalius faced skepticism from older physicians who questioned his integrity. Galileo endured a trial. Copernicus hesitated until his death was imminent. Their ideas unsettled more than academic circles. They challenged the foundations of theology, social order, and inherited power. What united them was not invention from nothing but the courage to replace citation with measurement and argument with demonstration. By the 17th century, that courage extended into biology and chemistry. William Harvey traced blood circulation through the pumping heart, overturning Galen's centuries-old humoral theory. Robert Boyle revealed the properties of air, demonstrating that it had weight and shape, while rejecting Aristotle's 4 elements and the promises of alchemy. Their work followed a consistent pattern, defining nature as a mechanism and seeking its principles through observation and experiment. Together, these architects of change were builders rather than rebels. They laid the frameworks for others to stand on and build upon. Their methods shifted knowledge from commentary on ancient texts to direct engagement with the world. They did this not because Europe lacked clever people before them, but because they chose to bring doubt into the open. In doing so, they left models of inquiry still recognizable today. Their approaches varied. Copernicus calculated, Vesalius dissected, Bacon advocated method, Galileo pointed telescopes, Kepler solved ratios, Descartes defined reason. Yet all moved in one direction, away from symbolic certainty and toward evidence-demanding observation. It was this shift that turned isolated insights into a revolution. While they forged new ways of thinking, another revolution was taking shape. The world around them, plants, animals, and landscapes, was being studied with equal intensity. The natural world, long regarded as an allegory, was opening as a book to be read. This rediscovery of nature would carry the same influence as their ideas, but through sight, sketch, and direct encounter with reality. Rediscovering nature involved asking new questions about the living world around us. For centuries, plants and animals had been depicted as symbols of virtues or as signs from myth, but Renaissance observers began to see them as they truly were. The change was revolutionary yet straightforward. Stop interpreting allegory and start recording reality. This new approach was partly driven by medicine. Herbal remedies were essential for treatment, and a doctor who confused one plant for another risked a patient's life. A sketch repeatedly copied from old manuscripts was no longer enough. What doctors and healers needed were accurate images of stems, leaves, and flowers that could be used in practice. Accuracy was no longer just decorative, it became practical. Botanical guides met this demand. Writers such as Otto Brunfels and Leonhard Fuchs published works featuring woodcut illustrations that accurately depicted what an observer could see in the soil and garden. Fuchs's De Historia Stirpium, published in 1542, was especially valued for its precise images, some of the most accurate plant drawings of the 16th century. For the first time, a printed image could travel across Europe and serve as a reliable aid, enabling people far apart to identify the same plant confidently. Observation was beginning to replace authority. Once plants were studied through images, they were also arranged in gardens specifically designed for educational purposes. Botanical gardens became teaching spaces where specimens grew alongside one another. No longer relying solely on texts, students could walk among living examples, test identifications, and compare structures. The study moved from books into the open air. In anatomy, nature revealed itself even more vividly. Dissection theaters presented the body not behind monastery walls, but in tiered public halls, where crowds could watch skin and organs being uncovered. These were not secret lessons, but open demonstrations that transferred knowledge from manuscripts to what could be seen and confirmed. Evidence was displayed, debated, and shared. The desire to catalog expanded to include everything that appeared strange or unrecorded. Naturalists compiled volumes aimed at listing every visible species, including beetles, birds, and fish, with drawings that were more descriptive than allegorical. These collections sought order through resemblance, grouping creatures by form rather than symbolic significance. It was a move towards classification, however tentative, guided by similarities and differences that anyone could verify. The arrival of new plants and animals from overseas further challenged old categories. Corn, potatoes, and tobacco, arriving from the Americas, had no place in ancient classifications. Plants and seeds from Asia and Africa were equally disruptive. Their appearance in Europe exposed the gaps in traditional knowledge. No ancient list could claim to be complete anymore. A single new fruit was enough to show how limited the ideas of Aristotle or Galen had been. Illustrations became essential for documenting these unfamiliar specimens. Words might struggle to describe shape and structure, but drawings captured qualities that words blurred. A sketch of a seed pod or a shell conveyed form instantly. In this sense, illustrations acted almost like instruments, extending the reach of memory and enabling comparisons across borders. Images standardized reality in ways that descriptive prose could not. The effects went deeper than mere corrections. Naturalists began to realize that the living world was more diverse than tradition had suggested. Old models assumed completeness, but as Europe observed more, it discovered increasing novelty. Catalog after catalog overflowed with unexpected shapes and structures. Nature was not repetitive. It was full of surprises, with each observation hinting at far more still unnoticed. This focus on detail altered the study's purpose. Instead of drawing moral lessons from animals or herbs, scholars approached them as evidence to be examined and analyzed. They dissected, described, compared, and experimented. The entire conception of nature shifted, from being a background for teaching virtue to being the subject of direct, repeatable observation. Every leaf vein, shell spiral, and organ became data to be weighed. By the late Renaissance, the book of nature was being read line by line through sight and specimens. Tradition gave way to what could be drawn, measured, and displayed. Students and physicians were encouraged to rely on what their senses confirmed rather than what centuries had preserved. A new steady habit emerged. Study began with evidence. That habit was soon extended upward. Once forests, fields, and bodies had been opened to inspection, thinkers started to ask whether the same empirical approach could be applied to the broader universe. If the tissues of plants and the flow of blood could be observed anew, what might be discovered by looking again at the heavens? For generations, the skies had been depicted as a set of perfect circles centered around Earth. To challenge this image was to challenge more than astronomy. It pressed against theology, hierarchy, and even identity. Yet in the mid-1500s, a few thinkers began to suggest that Earth was not a still center, but just another moving world. Leading the way was Nicholas Copernicus. A quiet man, he proposed a radical idea: place the sun, not Earth, at the center of motion. In De Revolutionibus Orbium Coelestium from 1543, he argued that the wandering paths of planets made sense if Earth itself was in orbit. What now seems routine was then a direct challenge to Aristotle's physics of fixed places and to church doctrine that placed humanity at the center of creation. Copernicus was not only adjusting the map, he was questioning the framework that upheld both science and faith. His book did not cause shock overnight. Many astronomers used his calculations without fully accepting his cosmos. His methods enabled more accurate predictions of where planets would appear, making them valuable for navigation and astrology. Astronomers such as Erasmus Reinhold developed tables based on his approach, which quickly spread for practical purposes. Yet the same men often refused to accept the heliocentric idea itself. The divide between employing his tools and accepting his worldview shows how reluctant people were to abandon ancient certainties, even as new methods improved accuracy. Then came Tycho Brahe, a nobleman, showman, and meticulous observer. Tycho did not adopt Copernicus's sun-centered model. Instead, he proposed a compromise where Earth remained stationary while the planets orbited the sun, and the sun, in turn, orbited Earth. Yet his true greatness lay not in this system, but in the records he left behind. Using large instruments of his own design, he produced star charts and planetary positions far more accurate than any previous records. Through years of nightly measurements, he compiled an archive of data that would prove invaluable. Tycho's model may not have endured, but his data became a foundation. Johannes Kepler inherited that treasure after Tycho's death. Initially convinced that planets moved in circles, he struggled when the data refused to fit. Patiently, he adjusted his assumptions until a new pattern emerged. The orbits were ellipses. From Tycho's observations, he derived 3 laws of planetary motion that captured how speed, distance, and orbital shape worked together. This was the first time mathematics and precise observation aligned across the entire solar system. Kepler demonstrated that harmony existed, but in ellipses and ratios, not in Aristotelian perfection. Galileo Galilei confirmed the new cosmos through direct observation. In 1610, his Sidereus Nuncius described what he saw through a telescope: mountains on the moon, dark spots moving across the sun, 4 moons orbiting Jupiter, and phases of Venus that only made sense within a sun-centered model. With each discovery, he dismantled parts of the old worldview. The heavens were not perfect, Earth was not unique, and motion was not limited to geocentric shells. These findings astonished audiences. Seeing moons orbiting another world, or rugged peaks on what was supposed to be a perfect sphere, made both scholars and church officials question long-standing truths. Taken together, these breakthroughs overturned an order that had persisted for millennia. Copernicus challenged the idea of a fixed universe. Tycho provided the precision needed to test any model. Kepler moved from inherited circles to the reality of ellipses. Galileo revealed a complex, physical cosmos with evidence impossible to deny. By 1600, Earth was no longer a stationary center around which everything revolved. It was itself moving, a planet among planets, within a sky governed by measurable rules. This new order brought both unease and opportunity. Humanity no longer sat at the pinnacle of the universe. Yet, this upheaval offered a gift. The heavens were now understandable. They could be predicted and tested, not accepted as opaque mysteries. For the first time, the same physical principles appeared to connect sky and earth. The cosmos seemed less like a stage set for human drama, and more like a system open to explanation. The revolution in astronomy did more than redraw planets. It compelled thinkers to ask how such truths could be established. Was discovery born from observation, measurement, and experimentation, or from starting with principles and reasoning them out? In the 17th century, this question would become pressing. Authority had weakened. The challenge then was how to establish certainty without it. Is knowledge derived from experience or reason? In the 17th century, this question was more than just a quiet puzzle. It was at the heart of a debate. Generations had learned through Aristotle's method, starting with abstract truths and moving down to specific cases. However, when observation revealed facts that didn't fit, another voice argued that knowledge must rise from evidence upward. The core issue was how to define truth itself. Francis Bacon clearly represented the empirical perspective. In Novum Organum, published in 1620, he dismissed scholastic disputes based on unverified assumptions. He claimed that the human mind contains idols, cognitive biases, and illusions that distort judgment. To overcome these, he recommended systematic data collection, experimentation, and careful inference. In this inductive approach, patterns only emerged after numerous observations, like stones building a wall. For Bacon, the purpose of learning was never mere talk. Knowledge equated to power, a means to harness nature and enhance life. René Descartes, on the other hand, sought certainty through reason. In Discourse on Method from 1637, he established a foundation on the one thing he couldn't doubt, the fact of his own thought. I think, therefore I am. From this starting point, he expanded outward by deduction, with each step grounded in clear and distinct principles. Descartes also provided science with new tools, developing analytic geometry that fused algebra with geometry. A curve could be translated into an equation, and vice versa. For him, structure did not begin with scattered fragments, but with a single keystone supporting the arches of certainty. The choice between these two approaches was profound. Could empirical reports from many experiments alone create order? Or was it necessary to have solid principles to avoid an endless list of facts? Trusting only data risked turning knowledge into a shapeless mass. Relying too rigidly on reason could freeze discovery under assumptions. The debate between empiricism and rationalism shaped 17th century thought across all fields. Mathematics became the bridge. Through analytic geometry, algebra gained the ability to describe curves, motion, and distance, giving form to phenomena once explained only with words. Numbers transitioned from simple tools of trade to the central language of natural philosophy. A thrown object could now be measured in terms of how far, how high, and at what speed. Logic and observation no longer need to remain separate. Together, they could build models of the physical world. This was more than just technique. It transformed how truth itself was approached. For centuries, certainty was regarded as the natural outcome of reasoned debate. By the mid-1600s, however, uncertainty became the norm. Each result was seen as provisional, subject to correction through further experimentation. Evidence could stand until displaced by more substantial evidence. Doubt shifted from a sign of weakness to the very catalyst of progress. Authority no longer held the final say. Religion was not absent from these changes. Many thinkers still believed in a divine order, but they also accepted that creation operated through consistent laws rather than constant intervention. To discover those laws was not to undermine faith, but to see the world's regularity as evidence of wisdom itself. Time and again, discussions about purposes gave way to a focus on mechanisms. The language of why was replaced by the discipline of how. From this long-standing tension, a compromise emerged. Observation, hypothesis, experimentation, reasoning, and replication formed a cycle. You started with what you could observe, posed a question, tested it, expressed the results numerically, and invited others to repeat the process. Truth was no longer a possession of authority. It became a process, careful, ongoing, and shared within a community. This pattern solidified into what is now known as the scientific method: calm, practical, and always capable of refinement. This approach overturned the culture of scholasticism that valued inheritance. Ideas were now to be tested, not preserved unquestioningly. Errors were expected and regarded as part of progress. What earlier centuries found astonishing would soon be routine in research. Propose, test, review, revise. Within this cycle, superstition and unquestioned authority could not endure. Claims required evidence, arguments demanded proof. The outcomes were lasting. Philosophy transformed into practical inquiry. Instead of seeking final purposes, scholars questioned function, process, and law. In place of unchanging inheritance, knowledge became iterative and subject to correction. What mattered was not whether a principle echoed tradition, but whether it withstood repeated testing. By the close of the century, this redefinition of knowledge had provided science with a new foundation. Inquiry had become both a method and a community, guided by observation and reason together. The question was no longer only whether truth emerged from experience or deduction, but how both could collaborate in uncovering rules that order the world. And with this framework of knowledge taking shape, another change was imminent. The tools that rendered this process precise were numbers themselves, symbols that transformed motion and matter into forms that reason could perceive. Equations would become new eyes, revealing patterns that were previously hidden from sight. In the 17th century, mathematics began to reshape how people understood the world. What had once been a craft for merchants or surveyors now became central to astronomy, navigation, and physics. Numbers no longer sat in the margins as convenient tools. They became the framework of knowledge itself. With this shift, the natural order stopped being described solely in words and began to be expressed through symbols and calculations. François Viète was one of the first to demonstrate how numbers could form a language. In 1591, he introduced an algebraic notation that used letters to represent both known and unknown values. Instead of restating each problem with complete sentences, he created a shorthand that revealed hidden patterns. A missing side of a triangle or the length of an angle could be symbolized and then solved using rules applicable across many situations. By turning problems into symbols, Viète provided mathematics with a flexible grammar, allowing insight to travel from geometry into physics and beyond. John Napier faced another challenge: the overwhelming burden of endless calculation. Astronomers charting planets or navigators planning voyages had to multiply and divide large numbers by hand, a task that could take weeks to complete. In 1614, Napier introduced logarithms, a system that converted multiplication into addition and division into subtraction. It was like transforming long division into quick steps along a shorter route. Kepler praised it as a miracle because it significantly reduced the labor involved in astronomy. With this tool, navigators could prepare tables in time to guide voyages, and surveyors and merchants could work more efficiently. Freed from tedious arithmetic, thinkers could concentrate more on ideas rather than sums. René Descartes further advanced the union of number and space. In 1637, he published Geometry, where he described a system now known as Cartesian coordinates. Every point could be marked with two numbers, plotted on a grid. Curves and shapes could now be expressed through equations, while equations could be visualized as curves. This link between algebra and geometry transformed the study of motion. A falling object could be plotted as a parabola on paper. Planetary orbits could be described in the same language. Descartes offered scientists a way to visualize motion clearly, turning dynamic processes into predictable forms on a page. Bonaventura Cavalieri explored new territory with his method of indivisibles. By viewing shapes as collections of infinitely thin slices, he could estimate areas and volumes that traditional geometry couldn't handle. It was a step towards calculus, though the complete theory was developed later. Cavalieri's method demonstrated that mathematics could reach into the infinite, not just the finite, and still produce practical results. Pierre de Fermat, studying tangents to curves, moved closer to the principles of differentiation. His ideas paved the way for measuring slopes and change, essential for describing motion. Simultaneously, his interest in numbers drew him into what we now call number theory, leading to conjectures that remained significant centuries later. Fermat's work suggested that mathematics was not solely about solving immediate problems, but also about discovering structures beneath surface-level questions. Blaise Pascal shifted focus to another aspect: chance itself. Investigating games and wagers, he developed a framework for probability. What appeared random became measurable through the use of fractions and ratios. He also introduced his famous triangle, a clever way to display combinations and outcomes. Although rooted in gambling, probability implied that uncertainty could be calculated. Over time, This evolved into statistics, now vital in medicine, economics, and scientific experiments. Pascal's insights revealed that mathematics could describe not just certainty, but also risk and unpredictability. Collectively, these innovations represented more than mere clever tricks. Viet established algebra as a language. Napier eased calculations with logarithms, accelerating progress in astronomy and navigation. Descartes fused algebra and geometry to describe motion with precision. Cavalieri and Fermat looked towards infinity and change. Pascal unlocked the potential of numbers to model chance where none was thought to exist. Each advance chipped away at Aristotelian philosophy, replacing verbal debate with testable, numerical evidence. For those living in the 17th century, the effects were immediate. Tables could be generated more quickly. Orbits could be charted with greater accuracy. Shapes, volumes, and slopes became measurable. Even uncertainty gained a mathematical form. Science began to advance more efficiently, supported by precise methods rather than mere speculation. Mathematics now provided proof where words could only persuade. By the middle of the century, mathematics had become the language through which scholars explained natural order. To discuss astronomy, mechanics, or trade seriously meant using symbols and equations. Numbers were no longer servants of philosophy. They were the foundation on which explanation itself stood. Each falling stone, orbiting planet, or spinning wheel could now be described with quantitative laws. That shift pointed towards a new kind of science. Once numbers had set the stage, the next challenge was not only to describe form and motion, but also to uncover the forces that caused them. As investigators began asking these questions, nature's hidden powers started to reveal themselves. Drop a ball, and it falls. For Aristotle, this was not a question, but a certainty. He claimed bodies descended to their natural place, with heavier ones falling faster because their essence pulled them more strongly. That view guided teaching for nearly 2,000 years. By the late 16th and 17th centuries, however, experiments began to speak louder than philosophy, and the story of motion underwent a change. Galileo Galilei made the first decisive break. Instead of relying on statements, he set up ramps and timed rolling spheres. By slowing the motion enough to measure, he revealed that all bodies fall with the same acceleration, regardless of their mass. Falling was no longer a matter of inner purpose, but of measurable force acting equally. He demonstrated that acceleration was not a vague quality, but a definable, uniform rate that could be measured and predicted. With that, falling stones became subjects of physics instead of mysteries of nature. These insights soon widened. If objects fell through the air, then what was the air itself? Aristotle insisted a vacuum could not exist. Without matter, he said, there could be no motion at all. Galileo's student Evangelista Torricelli challenged this idea directly. In 1643, he filled a glass tube with mercury, inverted it into a dish, and watched part of the liquid sink. A void formed at the top, and a stable column remained. The result astonished scholars. The space was an absolute vacuum, and the column stood only because the atmosphere pressed on it. Torricelli's barometer gave air a measurable weight. More dramatic still was Otto von Guericke's display in the mid-1650s. Using a pump, he removed air from two joined bronze hemispheres until only external pressure held them shut. Teams of horses strained to pull them apart, but the spheres would not separate until air was restored. The force of the atmosphere became visible in a way no argument could rival. A crowd did not need philosophy, to see pressure hold metal against metal with immense power. With these instruments available, Robert Boyle and Robert Hooke began to test gases in controlled ways. Working with Guericke's pump, they found that compressing air increased pressure, while allowing it to expand reduced pressure. In 1662, Boyle published the principle now called Boyle's law. At constant temperature, the pressure of a gas is inversely proportional to its volume. Air behaved as if it were a spring, elastic and obedient to measurable rules. They also examined the role of air in life and fire. Sealing animals and candles inside evacuated vessels, they observed that both life and combustion stopped. While this did not directly reveal oxygen, it showed that only part of the air supports breathing and burning. What was thought to be a simple element turned out to be more complex. Air was not just one thing, but a substance with properties that could be separated and studied. For Boyle, these findings challenged more than individual claims. They eroded the doctrine of the four elements. Matter is no longer divided neatly into earth, air, fire, and water. Instead, it appeared to be made of unseen particles whose behavior could be tested. While still far from modern atomic theory, this corpuscular philosophy opened the door to experimentation in chemistry. Matter became measurable and governed by laws, linked to mechanical philosophy rather than mystical essence. Simultaneously, Christian Huygens focused on motion with equal precision. He investigated collisions, pendulums, and impacts to uncover patterns of conservation. His pendulum clocks provided Europe with the most accurate timekeepers yet, enabling motion to be measured with greater precision. By describing how bodies rebounded and momentum transferred, Huygens turned vague ideas of impact into consistent laws that anyone could verify. It was no longer enough to explain why things moved. What mattered now was how. The bigger picture was striking. Gravity pulls with uniform acceleration, not variable essence. A mercury column stood because air exerted pressure against it. Bronze hemispheres held together because atmospheric pressure surrounded them. Gases rose and fell in pressure following precise ratios. Pendulums swung with predictable timing. Invisible forces became visible through experiments, displays, and measurements. By the mid-1600s, the transformation was evident. Physics had broken free of words about purpose and natural order. It had become a discipline of law, ratio, and demonstration. Claims were tested publicly and published for all to debate. Invisible powers, gravity, air pressure, elasticity, were no longer mysteries but measurable realities. Each could be expressed as a rule, reproducible with the right tools. While motion and matter were being redefined in this way, another field was also undergoing its own upheaval. For centuries, explanations of the human body relied on the concept of humors and balance. But as the scalpel and microscope entered the classroom, traditional certainties in medicine faced the same challenge that physics had already faced. For centuries, doctors explained illness through the shifting balance of four humors: blood, phlegm, yellow bile, and black bile. A fever was seen as excess heat in one fluid, or melancholy as too much of another. This model guided medicine for over a millennium. By the 1600s, sharper tools for dissection, measurement, and magnification began to test and overturn these ideas. The emerging picture was no longer fluid and allegorical, but mechanical and structured. Andreas Vesalius was the first to make a decisive break. Trained at Padua, he set aside Galen's texts and turned to the human body itself. In 1543, he published De Humani Corporis Fabrica. a detailed atlas of anatomy based on his dissections. Standing before students, he cut open cadavers and revealed that Galen, who had relied on animals, was often mistaken. The human jaw was a single bone, not two. The heart's wall showed no hidden pores. These corrections, presented in striking engravings, treated anatomy as something to be seen directly, not inherited from books. His work sparked outrage among conservative scholars. To question Galen was to accuse generations of error. Yet the precise drawings in the Fabrica spread rapidly through Europe. Physicians trained with Vesalius's images began to cut and observe for themselves. Each incision became a test of fact, not an act of deference. Anatomy became a living science rather than a branch of commentary. William Harvey advanced this shift from structure to function. Trained in Padua, like Vesalius, he inquired about how blood circulated through the body. Galen had envisioned two separate systems, veins and arteries, with the liver continuously producing fresh blood. Harvey doubted this could be correct. Using careful experiments, he tied off vessels with ligatures and observed the results. He also calculated blood flow, the amount ejected from the heart each beat, multiplied by the pulse rate, was far too great to be replaced by liver production. From this, he concluded that blood circulated in a closed loop, pumped endlessly by the heart. In 1628, he published his results in De Motu Cordis, on the motion of the heart and blood. For the first time, physiology was measured and explained as a mechanical process. The claim unsettled many. To suggest that the heart was a pump seemed to strip away mystery and reduce life to a mere mechanism. Yet Harvey's logic and figures were unanswerable. Circulation explained the data better than ancient models ever could. It unified calculation and experiment into a single act of medicine. The old system of ebbing humors was no longer credible. New instruments deepened this shift. The microscope allowed tissues to be seen at scales too small for the naked eye. In the 1660s, Marcello Malpighi studied frog lungs and identified tiny vessels, capillaries, that carried blood between arteries and veins. This was the missing piece that confirmed Harvey's theory of circulation. The body's loop was now visible through the glass. Robert Hooke made microscopy accessible to a broader audience. His book, Micrographia, from 1665, contained detailed engravings of insects, plants, and tissues magnified many times over. Hooke coined the word cell to describe the small compartments he observed in plant tissue. The book revealed an unseen world of complexity and captured the public imagination. Readers marveled at the intricate order apparent in everyday objects. Microscopy turned the invisible into evidence. Every dissection, every slide under a lens, reinforced a new way of thinking. The body appeared less like a sack of unbalanced fluids and more like a network of parts, pumps, vessels, tissues, and connections, each with a specific function. Physicians began to focus on organs and processes rather than humoral balance. Chemistry entered medical practice, suggesting that compounds acted on tissues in a predictable manner. Disease was no longer seen as an imbalance. It was a failure of structure or mechanism. Between 1543 and 1680, biology evolved into a science grounded in evidence. Vesalius revealed the proper form of the body with his Fabrica. Harvey traced the circulation of blood under pressure, using numbers to substantiate his observations. Malpighi identified the capillaries that linked the theory together. Hooke presented hidden architecture to the public and introduced enduring terminology. Each development weakened Galen's authority and made living bodies as measurable as planets or falling stones. the impact was more than medical. It redefined life itself as a system governed by physical laws. Hearts were compared to engines. Blood obeyed circulation. Cells became recognized as the building blocks of tissues. The shift placed humans within the same natural order that physics and astronomy were steadily uncovering. By the end of the century, the body had been reconstructed in science as flesh and blood governed by mechanisms. As the understanding of nature inside the body grew, so too did the knowledge of nature beyond it. Once more, observation was forcing reality into a new framework, this time in the night sky, where the heavens themselves would no longer appear perfect or unchanging. Once, the night sky seemed eternal, perfect, and immune to decay. Stars were thought to be fixed in crystalline spheres, while planets glided in flawless circles. But evidence soon challenged this view. In 1572, Tycho Brahe recorded a brilliant new star, a supernova, that appeared suddenly where no change was supposed to happen. Then, in 1577, he measured a comet and showed it cut well beyond the moon, moving through regions Aristotle had declared solid and unchanging. These events shattered the old belief that the heavens were untouched by time. The telescope pushed this challenge further. When Galileo turned his lens to the moon, he found not a smooth orb, but a landscape of mountains and craters, their shadows shifting with the sun. It was terrain, no different in principle from landscapes on Earth. Soon after, he saw dark patches on the sun itself. These sunspots grew, shifted, and disappeared, revealing that even the brightest light in the sky is subject to change. The heavens were no longer perfect, they showed scars. Such discoveries broke down the clear divide between celestial and terrestrial. If the sun bore blemishes, if the moon had peaks and valleys, then the sky was not made from a purer substance than Earth. Galileo also found 4 moons orbiting Jupiter, a system within a system. That sight alone weakened the claim that all things must orbit Earth. The heavens, box by box, began to resemble the patterns familiar closer to home. Galileo explained this shift simply. Terrestrial physics can explain celestial phenomena. Causes acting on Earth, such as gravity, inertia, and motion, also govern the skies. The doctrine of uniformity implied these laws extended upward without exception. A falling stone and an orbiting planet belonged to the same story. This idea extended physics beyond Earth and gave astronomy a new foundation. Kepler put numbers to this story. Using Tycho's detailed records, he discovered that planets moved not in perfect circles, but in ellipses. Their speeds changed along their paths, accelerating as they approached the sun and slowing as they moved farther away. These motions were precise and predictable, explained by 3 laws that described orbital shape, timing, and ratios. The elegance lay not in divine circles, but in mathematical consistency. Observing from Earth, Kepler demonstrated that planets moved according to predictable rules. Comets highlighted the point. They traced sweeping, irregular paths, disregarding crystalline shells or uniform motion. With their blazing tails, they pierced regions once deemed impassable. Each sighting served as tangible proof that celestial perfection was a myth. If comets could cross the heavens unimpeded, then the very architecture of spheres dissolving into space must be false. These wanderers demonstrated that the sky obeyed laws of change, not divine unchangeability. Together, the moon's mountains, the sun's spots, Jupiter's moons, Kepler's ellipses, and the comet's trails blurred the line between above and below. Earth reflected light like any planet. Other planets host satellites, just as Earth has the moon. The exact measurements are applied across both domains. Instead of a divided world, there appeared to be a continuous system governed by ratio, law, and cause. What emerged was a profound shift. The sky ceased to be a realm of perfection, separate from decay. It became part of the natural order, accessible to the same scrutiny as oceans and rocks. Observers began to measure celestial changes with the same care as tides or falling objects. Telescopes, records, mathematics, everything contributed to shaping a unified cosmos. A once sacred mystery had been translated into trajectories and equations. This transformation did not remove wonder from the night sky. It changed its meaning. No longer a spiritual dome enclosing Earth, it was now a vast expanse structured by law. Each irregular comet, each blemished sun, each planetary eclipse revealed not disorder, but a system open to calculation. Astronomy was shifting from speculation to physics, from belief to demonstration. By the mid-17th century, the barrier between Earth and heaven had disappeared. The exact causes, forces, and measurements are applied everywhere. With that realization, a new question arose. Could one mind unify these scattered results into a single explanation? Isaac Newton entered this landscape with a vision that brought order to what had seemed scattered. His achievement was to unify the falling bodies, tides, and orbits of planets into a single explanation. Where earlier thinkers had offered fragments, he provided a framework that connected them. In 1687, he published the Philosophiae Naturalis Principia Mathematica, or for short, Principia Mathematica. That work has since been recognized as the pinnacle of the scientific revolution. The Principia Mathematica presented three universal but straightforward laws of motion. First, a body remains at rest or in uniform straight-line motion unless acted upon. Second, the force acting on an object is equal to its mass multiplied by acceleration. Third, every action has an equal and opposite reaction. These laws were few, yet they applied to all matters. With them, Newton replaced a patchwork of examples with a universal system. The physics of an apple was also the physics of the moon. At the core of his system was an even bolder concept, the law of universal gravitation. Newton argued that every particle of matter attracts every other particle. The strength of this attraction is proportional to their masses and decreases with the square of the distance. With this simple formula, he unified phenomena that had resisted explanation for centuries. The fall of a stone, the orbit of planets, the return of comets, and the rhythm of the tides all became manifestations of a single force acting everywhere. The universe became understandable as a single mechanical system. To illustrate this, Newton imagined a cannon on a high mountain. Fired gently, the ball drops to the ground. Fired faster, it travels further before hitting Earth. Fired even quicker, it never lands. Instead, it curves endlessly around the planet. The same gravitational pull that causes objects to fall also keeps celestial bodies in motion. What changed was not the principle, but the speed and distance. The weight of objects on Earth and their orbits in space were two sides of the same interaction. This perspective also explains why Kepler's planetary laws were effective. Kepler described ellipses, varying speeds, and patterned orbits. Newton demonstrated that these were not isolated observations, but rather the result of the inverse square law. Kepler's empirical laws were revealed as outcomes of gravitation. One mathematical principle unified the mechanics governing Earth with the paths of planets around the Sun. This unity dissolved the last boundary between above and below. Newton did not embellish this with speculation. When challenged to explain how such an invisible action at a distance might work, he dismissed further guessing. "I frame no hypotheses," he said. For him, it was enough that the numbers matched the evidence. Gravity needed no hidden essence, no invocation of spirits. It was accepted because it explained phenomena with accuracy that could be tested and confirmed. The Principia Mathematica held predictive power as well as explanation. Newton calculated that Earth should not be a perfect sphere, but should bulge slightly at the equator due to its rotation. Decades later, expeditions measured this flattening and confirmed his prediction. He also demonstrated how this shape, pulled by the sun and moon, accounted for the slow precession of the equinoxes. Such results reinforced the idea that a universal law could extend to phenomena once thought beyond understanding. What Newton presented was not merely new knowledge, but closure to a long quest. Galileo's experiments with falling bodies, Descartes' mechanical philosophy, Kepler's orbital laws, all were integrated within a single framework. Even the irregular return of comets fitted into this principle. Fragments that once seemed incomplete now contributed to a coherent structure. Evidence was no longer isolated. It was recognized as stemming from deeper rules. The impact was profound. The universe appeared as a vast machine governed by mathematical order. From an apple's fall to the turning of planets, one set of laws sufficed. Theology was no longer required to explain planetary motion. Their movements could be demonstrated through geometry and calculation. The heavens ceased to be a mystery and instead became an open domain for science. This is why Newton's Principia Mathematica is often regarded as the moment when natural philosophy transitioned into modern science. With mathematics at its core, nature could be predicted, not just described. The language of law applied equally to distant stars and familiar ground. Authority now rested on both calculation and evidence. This quiet shift in standards defined the science that followed. Yet, this triumph did not erase older ways of thinking. Belief and superstition persisted, even as experiments and laws advanced. What Newton achieved demonstrated how far reason had traveled, but around him, Europe still clung to traditions resistant to change. Even as telescopes and equations transformed how people viewed the universe, old beliefs continued to influence daily life. The same decades that produced precise instruments and printed discoveries also saw fears of witches, belief in horoscopes, and searches for hidden elixirs. These remnants of belief persisted alongside scientific progress, becoming woven into the same culture. The witch trials are perhaps the clearest example. Between 1550 and 1700, thousands of women were accused of serving dark powers, and many were executed. Communities explained disease, poor harvests, or sudden misfortune through neighbors believed to be agents of Satan. Courts examined bodies for supposed devil's marks and accepted rumors as evidence. Such actions were not limited to remote villages. They were approved by church and state, which lent authority to fears that most people found convincing. The scientific revolution offered new explanations, but these had a limited reach beyond small intellectual circles. For most villagers, older traditions still outweighed the distant claims from newly printed books. Astrology also thrived. Its roots went back to antiquity, but in the 17th century, it remained an integral part of everyday life. Princes consulted astrologers before traveling or engaging in conflict. Physicians wrote horoscopes to determine the best times for treatment. The sky was interpreted as a clockwork of signs that could guide human affairs. Even leading astronomers saw no contradiction. Johannes Kepler and Galileo Galilei both prepared horoscopes while also charting planetary motion mathematically. To them, the heavens could be measured and interpreted in parallel ways. Astronomy and astrology overlapped, reflecting the blurred boundaries between reason and belief. The same was true of alchemy. Its aims sounded mystical, to turn base metals into gold or to create a universal medicine, yet its practices, namely heating, distilling, and testing materials, also laid the groundwork for modern chemistry. Robert Boyle, regarded as a founder of contemporary chemical science, began within an alchemical tradition. Isaac Newton himself invested significant effort in deciphering texts and recipes in search of the hidden truths of matter. To dismiss this as folly overlooks its central importance at the time. For Newton, studying gravitation and alchemy was part of one continuous pursuit, uncovering the universal laws written into creation. Alchemy was not opposed to science, but one of its older languages. This coexistence of old and new created a landscape of contradiction. A doctor might mention William Harvey's discovery of blood circulation one moment, yet consult a horoscope for diagnosis the next. Astronomers described comets mathematically, but also regarded them as omens. For villagers, the idea of malicious neighbors wielding harmful magic seemed more immediate than abstract scientific ideas like atmospheric pressure or elliptical orbits. Knowledge advanced in universities and academies, but in daily life, fear and tradition remained powerful. Institutions started shifting the balance. When the Royal Society of London was established in 1662, it emphasized reproducible experiments. Its motto, nullius in verba, meaning take nobody's word for it, embodied the new ethos. Authority no longer rested on books or masters, but on demonstrations that any member could reproduce. Boyle's air pump or Hooke's microscope were credible because others could observe the same results firsthand. This culture of repeatability gradually diminished the influence of mystical explanations. Astrology and alchemy did not disappear overnight, but they waned in importance as collaboration and published evidence gained prominence. However, adoption was inconsistent. Most Europeans were uneducated and lacked access to observatories or pumps. Their guidance came from sermons, neighbors, and traditions that felt accessible. Horoscopes persisted in homes long after telescopes revealed moons orbiting Jupiter. Wise women brewed remedies influenced more by folklore than experimentation. The new science communicated through languages of circulation, vacuums, and ellipses that few understood. Old beliefs persisted simply because they provided explanations aligning with everyday experiences. Even among the educated elite, superstition lingered. Newton performed planetary gravitation calculations by day, then studied alchemical texts and biblical prophecy by night. This was not hypocrisy, but representative of the era's blurred boundaries. Knowledge was rarely categorized neatly. Rational inquiry and mystical pursuits shared desks and minds. Many figures advancing modern science carried older frameworks within them, reminding us that belief and evidence often coexisted in the same person. The transition was gradual, not abrupt. The boundaries of science solidified slowly as journals, academies, and shared standards made it increasingly difficult for astrology and alchemy to claim authority. Witch trials declined as courts and clergy adopted skepticism. Astrology, once prominent in princely courts, became increasingly marginal. Alchemy transformed into chemistry as reproducibility demanded procedural clarity. Superstition did not vanish, but it was gradually pushed aside from intellectual life and lost its former influence. What science gained during this period was permanence. Instead of being linked to individual thinkers, results became part of a collective structure to defend knowledge from the pull of older beliefs. This shift was neither instantaneous nor absolute, but was crucial in shaping the endurance of ideas. It set the stage for something vital. To ensure discoveries endured, they required more than daring individuals. They needed communities, rules, and institutions capable of carrying fragile insights beyond the lives of their creators. By the mid-1600s, the practice of science was shifting from private letters and guarded notebooks into something much more visible. This was the moment when science became public, embedded not only in the work of individuals, but also in institutions that made discovery enduring. The Royal Society of London was the clearest example. It grew from informal gatherings at Gresham College in 1660 and received its royal charter in 1662. Its motto, Nullius in Verba, summed up the change. Authority no longer rested with ancient texts or clerical approval. What mattered was whether an experiment could be demonstrated and repeated. At the Society's early meetings, members like Robert Hooke staged demonstrations in front of their peers. Results that might once have been whispered in letters now became shared experiences. Science stepped out of secrecy into a space where many could examine the evidence together. The Royal Society gave credibility to results in a world filled with claims. In 1665, it launched the Philosophical Transactions, the first continuous scientific journal. These printed pages contained accounts of experiments, astronomical observations, natural histories, and reports from travelers. Instead of vanishing into personal notebooks, discoveries became public records. Copies traveled across Europe, enabling others to read, repeat, and respond. Replication became standard. A claim only carries weight if someone else could achieve the same result. What had once been accepted on reputation now stood or fell on evidence. This sharing transformed the rhythm of inquiry. A theory that could be tested elsewhere persisted, one that could not soon lose influence. Journals preserved ideas beyond the lifespan of their authors, turning them into a lasting resource. Knowledge became portable across distance and time. On the continent, France pursued a different model. In 1666, Jean-Baptiste Colbert founded the Académie des Sciences under King Louis XIV. Unlike London's voluntary society, the Académie was established as a government body from the outset. Housed in the Louvre, it organized scholars into regular programs and often directed their research towards state tasks, such as surveying lands, refining maps, and improving engineering. Its prestige spread throughout Europe as a symbol of precision and order. While the Royal Society thrived on openness and debate, the Academy demonstrated how state patronage could provide resources and stability for inquiry. Despite their differences, both institutions aimed for the same goal, structuring science. In London, credibility grew through shared demonstrations and standardized evidence. In Paris, the public authority rooted the investigation in state power. Together, they marked a shift where science no longer depended solely on brilliance, but on systems designed to preserve and test results. This example proved contagious. Smaller groups, academies, and correspondence networks spread across Europe. Even when scholars were separated by language or politics, they could still compare findings via published accounts. Peer review emerged in its earliest form. New ideas were no longer private property, but objects of collective scrutiny. Even controversial or incomplete claims could be openly aired, debated, or refuted, rather than kept hidden. This reversal changed both motivation and method. For centuries, some thinkers hoarded results, fearing others might steal their discoveries or profit from them. Now, recognition came through publication. Credit was given to the first to share, not the first to hide. The culture of secrecy weakened under the influence of journals and institutions. Openness allowed ideas to have a life beyond a single author, which is why discoveries began to outlast their creators in a permanent record. The effects extended beyond laboratories. Societies redefined what it meant to own an idea. When you published, you did not give your work away. You secured your claim by making it public, enabling others to test and expand upon it. Discovery belonged to both the individual and the wider community. This collaborative model became the foundation of modern science. The achievements of these new structures were evident. They made knowledge accessible. Printed journals, academies, and networks guaranteed that even fragile sparks of discovery survived. Results became reproducible, portable, and open. Across Europe, science ceased to be the property of isolated individuals and transformed into a collective endeavor. And yet, this story did not end within Europe's borders. The exchange of knowledge, plants, instruments, and ideas was already extending far beyond royal academies and city societies. The next phase of the revolution unfolded through wider connections via trade, exploration, and encounters reaching across the world. Although history often portrays the scientific revolution as a European triumph, its foundations extended much further. The mathematics, instruments, and observations used by 17th century thinkers originated from centuries of cultural exchange. Translation, preservation, and trade facilitated the exchange of ideas across languages and continents. Without these global contributions, Europe's so-called revolution would never have taken the shape we now recognize. Arabic scholars played a vital role in conserving and expanding ancient knowledge. During the Middle Ages, they translated the works of Greek mathematicians and philosophers into Arabic, ensuring that texts on geometry, optics, and medicine were not lost. They built upon these, particularly in algebra, refining concepts that Europe would later adopt. Alongside this transmission came the Indian numeral system, introduced to Europe through Arabic scholars. The inclusion of zero and place value replaced cumbersome Roman numerals, enabling once impossible calculations. Every subsequent achievement in European mathematics was built on this quiet inheritance. Chinese traditions also left a profound mark. The magnetic compass, improvements in timekeeping, and long-standing astronomical records all originated from China and reached European awareness. Chinese scholars created detailed star maps and calendars with accuracy celebrated across cultures. These records showed that the heavens could be observed with precision. Coupled with European instruments, they inspired new methods of celestial measurement. The story of the telescope follows a similar pattern, an innovation shaped by centuries of cross-cultural exchange. From the 15th century onwards, however, exchange often took a less friendly form. Voyages of conquest and colonization supplied European science with a variety of specimens. Ships from the Americas, Africa, and Asia returned with unfamiliar foods, minerals, and plants. Bananas, cocoa, tobacco, maize, and potatoes challenged the categories inherited from Aristotle and Galen. Herbalists and physicians encountered remedies foreign to their traditions. Each discovery pushed natural history to expand, yet also revealed that this growth was closely linked to conquest and forced encounters. Intellectual progress was, to a significant extent, driven by the extraction of knowledge. Jesuit missions provided another avenue for scientific dialogue. Travelers in Asia and the Americas carried instruments, mathematics, and astronomical models back to Europe, while returning with knowledge that was otherwise inaccessible. In China, Jesuits like Matteo Ricci collaborated with scholars at the Ming and Qing courts. They introduced European astronomy and mathematics, demonstrating the use of telescopes and new planetary systems. Simultaneously, they reported back calendrical and medical knowledge from their hosts, feeding these observations into European academies. The outcome was not a one-way transfer, but a dialogue shaped by uneven power. Both sides contributed, though the terms were seldom equal. The influence of the empire was particularly evident in the field of natural history. Early collections of curiosities displayed dried plants, shells, minerals, and animal specimens gathered overseas. Wealthy patrons and universities began to establish botanical gardens when rooms could no longer contain the volume of arrivals. These gardens became living archives where plants could be studied, compared, and taught. Crops from the Americas transformed both scholarship and daily life. Potatoes, which can grow in poor soils, became staple foods in maize-diversified agriculture. New remedies entered medicine. Each change demonstrated how the work of naturalists became intertwined with shifts in diet, farming practices, and public health. What Europeans studied was inseparable from what they consumed. This global rhythm raised questions of ownership. Exploration and conquest brought new knowledge into European hands. Specimens that had grown in local ecosystems for millennia were transplanted into glass houses far away. Published volumes presented these plants and animals as European discoveries, with little recognition of the communities that had used and understood them for generations. Knowledge was gathered with territory. Both were claimed as possessions. The flow of ideas was global, but credit often remained with European institutions. The pattern was paradoxical. Expansion broadened Europe's imagination, but the tools of empire limited acknowledgement. Arabic translations, Indian numerals, and Chinese records were integrated as if they were raw materials. Colonized lands provided collections later cataloged in European libraries and gardens. Within Europe, names like Galileo and Newton became symbols of progress. Beyond Europe, the vital contributions of scholars, sailors, and local traditions often faded into footnotes, if mentioned at all. And yet, from a broader perspective, the scientific revolution cannot be separated from this global input. Its mathematical tools drew upon Indian and Arabic inheritance. Its observational practices were refined with Chinese instruments. African, Asian, and American specimens reshaped the natural history of these regions. The enterprise we call European science was, in truth, rooted in the broader world. The system of publication and institutions in Europe consolidated authority, but they rested on foundations laid by distant hands. The legacy is inevitably complex. There was reciprocity, but also conquest. There was curiosity, but also hierarchy. The revolution's global input enriched everyone, but European institutions strengthened their reputation. Behind each celebrated figure stood generations of translators, collectors, and unnamed contributors. This tension leaves us with a question today. Was science during this period a universal expression of shared human inquiry, or a system shaped by exclusion and empire? In some sense, it was both. The scientific revolution was global in its origins, yet European in its ownership. That is the inheritance modern science still bears, built from worldwide flows of knowledge, but framed by institutions that later centralized recognition. And once you see this clearly, the shape of the revolution comes into focus. It was never just a story of instruments or individuals. It was humanity as a whole, revising its relationship with reality, an endeavor that now compels us to ask what it meant. and what kind of legacy it left behind. The scientific revolution was not a single breakthrough, but a gradual rewriting of nature's rulebook. Over the course of 2 centuries, thinkers have tested, measured, and replaced tradition with methods that still influence your life today. It was as much about courage as invention, defining truth as provisional, open to revision, and based on evidence. Its legacy has 2 sides: the power of a method that unlocked planets, bodies, and atoms, and the reminder that many voices were ignored in the process. When you question, test, and revise, you continue that same human pursuit